In the last set of lectures, we saw how we can use a simple probability model to describe some of the randomness that we observe in the real world, which leads to variation in the possible values we could observe. In any one experiment, we don't know what the outcome might be, but the probability model gives a structure to the chances of the possible values that we might observe. We were also introduced to the concept of a sampling distribution, which is the probability distribution for a statistic that we can calculate from some data, such as possibly a proportion or a mean. Now we're going to go back to starting with the real world, our data, and developing some inferential procedures so that we can say what we can about the theoretical world that we're interested in. To review the way we're thinking about data and the inferential process, let's look again at the underlying structure. In the real world, we have some observed data. These could be life expectancies or age estimates on skeletons, or counts of people developing HPV infections, or the sequence of heads and tails we get when we're repeatedly flipping a coin. We don't observe the theoretical world, but that's what we really want to understand, given the imperfect and incomplete information that we have in our real-world data. In the theoretical world, we might have a scientific model that describes the nature of the variables, and we have a statistical model that describes the nature of the variation or the probabilities associated with the variables and the statistics that we observe in the real world. We use the data from the real world in conjunction with the models we've devised in the theoretical world in order to make conclusions. Sometimes we think of the theoretical world as a population, from which we've observed a sample to get our data, and the goal is to make our inferences about the population based on that sample. When introducing probability, Jeff started by flipping a coin 10 times. We know that a coin is equally likely to come up heads and tails, so we'd expect to get 5 heads and 10 flips. That's what our scientific model in the theoretical world says. Indeed, the probability model for the number of heads when flipping a coin a fixed number of times has this distribution, which is called the binomial model, and which has expected value, or mean, of 5. The binomial model is our statistical model in the theoretical world. But of course, there's also some variance in the number of heads we might get in our 10 flips. We don't expect to get exactly 5 heads each time. Indeed, Jeff got 6 heads. This binomial model is our sampling distribution for 10 flips of a coin, where what we're interested in is the number of heads. We can see from this distribution that 6 is a reasonably likely value, and although it's possible to get 0 or 1, or 9 or 10 heads, these extreme values are quite unlikely. We could also think about this in terms of the proportion of heads. We'd expect to get 50% heads, or a proportion of 0.5. But 60% heads, as Jeff got in 10 flips, is reasonably likely. No heads or only 10% heads, or the other extreme, 90% or 100% heads, is quite unlikely. So we don't expect to get 5 heads every time, but 6 and 4 are quite possible. 3 and 7 could happen too. What's the limit? Where do we draw the line for the range of possible values for the proportion of heads that is what we'd expect to get most of the time? Back in the introduction to probability, Jeff also flipped a beer cap that was red on one side and silver on the other. In his 10 flips, the beer cap came up red 4 times. Now, if a beer cap is equally likely to come up red or silver on each flip, then the number of reds in 10 flips would have the same sampling distribution as the distribution for the number of heads when flipping a coin 10 times. And we can see that 4 is a possible value with a reasonable probability. But after just 10 flips, I wasn't convinced that 40% is a reasonable estimate of the proportion of reds when flipping a beer cap. Indeed, there seemed to me a lot of other plausible values for the proportion of reds. And even if flipping a beer cap is not 50-50, say there's only a 20% chance of getting a red cap, then we'd have this sampling distribution, which comes from another binomial distribution with 10 flips, but now a probability of 0.2 of seeing red. And getting 40% reds still seems reasonable. So I put Jeff to work, and I had him flip the beer cap 990 more times for a total of 1,000 flips. It took him a while, But he finished and got 576 reds in his 1,000 flips. So now we've flipped a beer cap 1,000 times and observed 576 reds. This is our real-world data. We have a statistical model for this situation. It's binomial again for the 1,000 flips. But this time, we don't know the probability of getting red on any one flip. So now the question is, what can we say about our beer bottle cap and the proportion of times it comes up red when flipped? We can estimate this proportion. We have an estimate of 57.6%. This is a statistic calculated from our data, and it seems like a reasonable estimate for our parameter in the theoretical world. But it would be good to say more. I don't really believe that it is exactly 57.6%, and I'd like to know a range of plausible values for the theoretical world parameter. I'd like to know if, based on these data, it could be as low as, say, 40%, or maybe as high as 60%. It may not seem like estimating the proportion of times a flipped beer cap comes up red is a pressing scientific problem, but this scenario is extremely common. Governments and political parties and the press regularly use polls to estimate the proportion of people who are going to vote for a particular candidate or who support a particular issue, such as whether or not we're willing to pay more tax from our subways. They survey a sample of people to make inference about a population. This is our observed data, analogous to our beer cap flips and how many came up red. And the parameter they're trying to estimate is the proportion of people who support the candidate or are in favor of more taxes in the population, corresponding to the true probability of a beer cap coming up red when flipped, what we might see if Jeff flipped it infinitely many times. Let's introduce one more example that we'll be using in the upcoming lectures. A facelift is a common cosmetic surgical procedure, and one of the goals of patients undergoing the surgery is typically to look younger. A few years ago, some surgeons came to the Statistical Consulting Service at the University of Toronto to ask for our help in quantifying just how much younger a patient might look after such surgery. They wanted to be able to tell their potential patients that, on average, people look X years younger. So they took photos of 60 patients just before their surgery and again 1 year later. Then for each photo, they asked 10 people to estimate the age of the person in the photo, and they averaged the 10 estimates together for a measure of the perceived age. How much younger a person looks post-surgery could then be measured as the difference in the perceived age for their before versus after photo, adjusted for the year that passed between when the photos were taken. So we have some real-world data measured on a sample of 60 people, and we'd like to make inferences about a theoretical world which includes the population of all facial plastic surgery patients. We can estimate the mean perceived age change, but we'd also like to know how precise that estimate of the mean is. If the surgery, say, makes people look 10 years younger on average, based on our data, do we think the theoretical world mean might be as high as 15 or as low as 5? So in addition to the estimate of the theoretical world mean, we need a range of plausible values for it. The topic of the next few lectures is confidence intervals, which are methods for giving a range of plausible values for our theoretical parameters, given the information we have in our data from the real world. As we go forward into inference, remember that in order to use inferential procedures, we need our data to either come from a randomized experiment or from a random sample from some population, or at least that we can think of as a random or representative sample of a population, collected without any bias. If there isn't any randomization, we don't have a probability model in our theoretical world, and our inferential procedures don't apply. And another note before we go forward, the inferential procedures that we'll be using for the next little while all assume that our data are independent. That is, there's no relationship between any of the observations. This is the most important condition that we need for inferential procedures. If we don't have independence, we need much more complicated methods.